That's a very nice alarm. Good morning, everybody, and we welcome you to the 7th session of the Quantum Technology Training for Policymakers. I will start sharing my slides right away, as you don't see my face actually, because I have my camera problem, but Leonardo has been volunteering for representing at least the start of this training with the visual, and we are very thankful for this. And now I hope you see my slides. So please, Leonardo, give me okay that you see slides.
Yes, we see the slides.
Great, that's very nice. So welcome to the training. And today we are going to talk about use cases of quantum technologies in quantum simulations. So we have two great speakers that I'm going to introduce shortly. And before we go further, please save the date. And the next session, and this is going to be the final one for this circle, unless we decide to add one more that is even more exciting, but this would be a surprise. And the next session will be on the state of the art of the quantum technologies, which means that we will have a look in our dreams, or what things are to come, what use cases are to come, and what is the strategic research and industry agenda for the quantum technologies in the upcoming year at least. And now that you will have saved the date for the 4th of April of this session on the state of the art of quantum technologies, we proceed with the one that we have just prepared for you. So as always, the CNR from Italy is coordinating the preparation of the sessions, and we are three people, and Professor Costanza Toninelli. I don't know what we have missed the right title here. She's coordinating the team, and me, I'm Oxana Mishina. I am the backdoor organizer of things, and Diana is doing the doctoral study in our team, and she is supporting us on many other things. And we thank very much the whole group of 𝐀𝐠𝐞𝐧𝐝𝐚 of Coordination and Support Action of Quantum Flagship for helping us in organizing these wonderful events. As always, we wish to inform you so that your decisions are best informed, and then that it helps you to cooperate with peers between the European Commission institutions and with other countries, and also empowers you for a more fruitful and more interesting discussions with experts in quantum technologies. So keeping this in mind, I just want to remind that usually we are very diverse. Here I'm showing you the participants from the previous training, and on the countries side we have participants from many countries. I think 21 was so far the record for us, 29 was so far the record for us. We obviously notice that some countries participate more than others, but we are very happy that this is Belgium, because this was the European Commission that kindly asked us to organize this training, and we see that they really profit very well. And generally, people who attend this training are very well informed and keep themselves updated, so we need to keep the quality of this training very high to satisfy them. Then, just a little bit about what types of policymaking our policymaking experts are attending this topic do. So most of them are in the government, and this is also what we have targeted in the first place. But we are very glad that we also have policymakers from other sides, from other type, like in the research and in the industry and in various different dimensions. So we are very proud, and today I'm happy to introduce you our first speaker, who is Professor Professor Leonardo Fallani, and he's a professor of physics at the University of Florence and the research assistant of LENS, which is the European Laboratory for Nonlinear Spectroscopy. And his research expertise lie in the field of experimental atomic and optical physics, and he's focusing practically on laser cooling, which is the heart of the cooking in this case, when we are talking specifically on quantum simulations. So also high precision spectroscopy, ultra cold quantum gases, disordered atomic system, and many body atomic physics. So at the University of Florence, he leads a research group which is exploring novel approaches for quantum simulations, which is the topic of the meeting today, and also with ultra cold 2-electron fermions. So they're integrating many body physics with methodological technologies for quantum control. So he has authored over 60 publications in international journals and books, and he has been invited as speaker at more than 60 international events. So in 2015, he was awarded an ERC Consolidator grant for the investigation of topological states of matter using synthetic ultra-cold systems. So we are very happy that Leonardo has accepted our invitation to prepare and to deliver you the presentation, which will do an overview and of use cases for quantum simulations in Europe at least, and probably also in the world. So Leonardo, welcome to the stage.
Okay, thank you a lot, Oxana, for the very nice introduction. So good morning to everybody, and it's a pleasure to be here and a big honor for me to be in front of your screen now, on your screen now. So I'll share my slides. So could you please confirm that you can see them?
Yes, they're perfect.
Okay, so in these the first 10 minutes of this webinar, I will give you an introduction to what quantum simulation is and some specific examples and use cases. And quantum simulation is one of the strategic application areas of quantum technology. So you have heard of communication, computing, and sensing and metrology in previous webinars. So today we will speak of simulation. And before telling to you what a quantum simulator actually is, let me first make a statement on the fact that it is important to have efficient ways to perform calculations of quantum properties of matter. So, as a matter of fact, nature is quantum, and also most of the technology in which our society is based is quantum. So let's think to chemistry or material sciences or devices. So all these different technological areas are really dependent on our ability to perform calculation of quantum properties and to design new systems with specific target properties. For example, if you want to design new molecules, new drugs, or materials with new properties or devices that can be either electronic devices or light sources, you need to be able to perform quantum calculations. And performing quantum calculation is extremely hard for classical computers. And let me give you an example that can serve as an introduction to the field of simulation, that is the following. So in material science, you have materials that can have some nice properties that then you can employ and take advantage of in applications. One class of interesting materials for application is superconductors, and there are materials called high-temperature superconductors that exhibit the property of letting an electric current flow without energy cost. And these materials at the moment do not exist at room temperature, so you need some kind of cooling to have this superconductivity materials. And in order to potentially design new materials that can exhibit this behavior at larger temperatures, and also to understand why this behavior really why it happens in matter. So it is important to develop models. And I will not enter any technicality here, but so people in condensed matter physics have worked out some simple models that can be explained the behavior of superconductors, but there is a problem. The problem is that if you try to calculate the properties of these models on a classical computer, you fail. And you fail because quantum mechanics is computationally very hard to be attacked by classical hardware. So just to give you some numbers to tell you what the numbers are, if you think of an extremely tiny piece of material with just 2 atoms, that is something that is really, really tiny, a fraction of a nanometer. So 2 atoms, so a material made by 2 atoms correspond to 4 different configurations for the electrons in this material. So if you consider a material made by 4 atoms, so now the number of possible quantum states for the electrons inside this material is 36. So if you take now 6 atoms, 400 configurations, 8 atoms, 5,000 configurations, and so on. So you can see that as you increase the size of your system, so the number of configurations that your material can have explodes exponentially. And if you consider a very, very minuscule piece of a material made by only 64 atoms, you realize that that memory capacity that you would need just to store in a hardware, in a computer, the quantum state of this very tiny piece of material is 10 to the 37 bytes. That is 1 million of a billion of times estimated data storage capacity of the entire world. So this tells you that there is no way to perform a numerical simulation of a material considering this explosion of the size of the storage capacity that you need for making calculations. So there is this idea of quantum simulation that is a smarter idea to perform calculation of quantum mechanics that was developed in the 80s by Richard Feynman, Nobel Prize winner for physics, that was speculating on the possibility of having a quantum hardware. So instead of performing these calculations on the structure of materials on a real classical computer, even a supercomputer would not make this job. So the idea is to build a machine that could solve the problem by using its quantum hardware. And so this is what I will tell you today. So I will present this idea of a quantum simulator that is a different way of performing calculations with a quantum hardware. And there are different kinds of architectures for quantum simulators, and you have heard of many different platforms in previous webinars too for quantum technology. So you can use atoms, you can use ions, photons, superconducting circuits, NV centers, quantum dots, spins, a lot of different platforms that are suited for different purposes. And in the frame of quantum technology, we are investigating all of them because all of them can bring interesting and useful results for science and for society. But for this, since I have limited time, I will just mention one of this platform that is the platform based on ultra-cold atoms. That is also the first architecture that was used and was considered for quantum simulators. And so maybe now this idea of a quantum simulator will become more clear because I will make a specific example. So what you see here is what we call an optical lattice. An optical lattice is a grid of light. So you can see here that you have laser beams and you have maxima and minima of light intensity. And so atoms, so when they are cooled by lasers, they can be trapped in the position where the light has a maximum intensity. So in this configuration that we can realize and engineer very carefully and very accurately in the lab, so we have particles which are ordered in a kind of ordered crystalline structure. And so this system that is our quantum simulator basically imitates the physics of a different quantum system, that is the physics of a material. In a material, a metal or a semiconductor, a piece of silicon or superconductor, whatever, you have the physics of electrons, which are particles that move in a crystal, and the crystal is made by the atoms of the material. And so you can see that these two systems resemble one the other. And so we can use this artificial system made by atoms trapped with laser light to imitate and simulate the physics that happens in materials. With Pro that we can tune very accurately all the parameters that of our simulator, so in order to study different regimes for our materials, and also, and this is the interesting thing, for realizing in a lab some prototype, a small prototype of material and device, so to study its behavior and its effect that then can be eventually translated into production. So we do this by using the tools of atomic physics. So we can use lasers, magnetic fields, and so this is a picture from one of our labs here in Florence. And here in the middle, you have this quantum simulator with the atoms trapped by light. So given the scope of this webinar, I will not enter too much into the details of what kind of models and specific models of physics we can realize in the lab. So I will give you some broader view on use cases in just a few minutes. Just let me say that this is a kind of mature technology already. So compared to quantum computers, to universal quantum computers that are still in a heavy development phase, quantum simulators can be regarded as a kind of dedicated quantum computers that are designed just for specific applications, but they have already demonstrated some interesting results. And just a very brief showcases of things that have been studied in the last 10, 20 years in this context. So starting from first experiments made in Europe, in Germany, and also here in Italy. We have studied how, for example, systems that can exhibit a metallic, a conducting behavior, can be tuned into insulators when you change some parameters in the system that can be either interactions or the amount of disorder, imperfections in the system. And you can probe these prototype of materials even with atomic resolution. So you can really see single atoms and see how they move in these artificial crystals. And so really see by eye, or almost by eye, so with a microscope, you can see the conduction properties and how current flows in these systems. You can, using laser light and manipulating atoms with laser light, you can perform a simulation of different kind of physics. For example, the physics of Josephson junctions, that is the physics that you have in superconductors, and so realize kind of systems that are called atomotronic devices, which are similar to electronic devices, but with atoms replacing the electrons. And this is the frontier of quantum simulation. Since less than 10 years, people have started to realize systems where single particles, single atoms can be trapped in arbitrary networks, as you can see here, by using what we call optical tweezers. So focused laser beams, we can trap single atoms and arrange them in the geometry we want. So, and this can be used in combination with the excitation of these atoms to realize and simulate in a lab many different kind of models that can be useful not only for physics, but also for general problems that can be optimization problems in which, for example, you want to optimize some process or some function, some energy cost. And so you use this quantum platform to perform the calculation for you. So I am now driving towards the end of this introduction. Let me just say that quantum simulation is a large part of European effort in quantum technologies, and let me just mention this big initiative funded in the frame of a quantum flagship that is a project, PASQUANS 2, that is on study the extension and the realization of a new class of quantum simulators that can be programmable and can advance the state of the art. And there is a nice collaboration here between academia and industry, with different companies also entering this game. So applications. So some of them I have already hinted in my the previous slides. So I mostly told you about the possibility of simulate material science, so realize prototypes of materials, and even connected to that, the possibility, and this is one very interesting direction, to realize what we call quantum chemistry. So to perform controlled chemical reactions, but also to use these platforms to compute the energy levels and the properties of molecules. That is, of course, interesting in the perspective of then designing new drugs, and that can be more efficient for certain processes. Then we have some fundamental interest, for instance, in the physics of what happens in nuclear reactions. And also, as I was mentioning before, especially with these new programmable platforms, one can also embed in this quantum hardware some problems that is not quantum, for example, problems connected to the logistics, so optimization of traffic flow or routing, or other logistic problems that can be mapped into some quantum models that can be realized in the lab rather than simulated on a classical computer. So this is my last slide, and here I put some remarks. And so first, quantum simulator. So again, what is it? Is a non-universal quantum computer. So it is a device that has something in common with quantum computer, but is designed to perform some specific job. And quantum advantage on these quantum simulators has already been demonstrated. And one point, one interesting point of this approach, and I not mentioned that before. So when I presented these ideas of quantum simulation, this is what people usually call an analog quantum simulation. So it's not, it is not a sequence of gates that you program on a quantum computer. It is really analog in the sense that you have a quantum system that imitates another quantum system. And so this has the probe that this kind of approach is intrinsically robust against several sources of noise, with respect, for example, to universal quantum computers, and in particular, so it is not crucially relying on error correction, that is instead very important for quantum computers. There are some use cases in both fundamental research, academia, but also for industry, and some of them I've already presented, and some of them will be for sure, and many of them will be for sure, are still to be discovered. And so the field is exploding as in other areas of quantum technologies. And so new proposals are coming on basically a daily basis. There are multiple architectures. So because of time and because also my expertise, I focus on the atomic platform, but there are different platforms based on trapped ions, photons, or superconductors that can target specific applications and other classes of models that can be simulated. Regarding the implementation of these ideas, quantum simulation is performed at academic environments, but also some companies also in Europe have started and are also leading the market. And it is important to, as for the other areas of quantum technologies, to ensure supply chain and also to foster developments and advancement in it, because quantum simulators rely on advanced classical technology. So both electronics, but also laser equipment, photonic devices, detectors, cryogenics. So it is important to research and develop new technical solutions that can foster the development of new quantum simulators in a kind of virtuous circle in which classical technology can help quantum technology that could feed back into classical one. And last 2 points that are important, also connected to quantum computation. So one point regards the standardization, since at the moment quantum simulators are kind of ad hoc machines that have been that can be built and resolve some kind of problem. So standards have to be developed in order also to interface different quantum simulators between them, or also quantum simulators with quantum computers or high-performance computers, because this job that a quantum simulator can do can be a standalone job, or in a probably more fruitful way, it can be also combined with classical computation. So you can think of a quantum simulator, a kind of coprocessor for a classical computation, or also in combination with quantum computers. Last point regards certification, and this is an important point. Certification means how can we be sure that quantum simulators provide the good result for the simulation. Of course, we can benchmark against some high-performance calculation on some system of limited size, so we can test our quantum simulators and see that they give the right result. And then, when we have certified them, we can extend it and use the quantum advantage to perform simulations that are not possible for actual current classical hardware. Okay, this was my last slide, so I would like to thank you for your attention, and of course I will be here to answer your question later.
Thank you very much, Leonardo, for this extremely powerful and intense presentation. So now we have got to the end of the presentations, and we have time for discussions. We've been collecting the questions and answers, so some of them were also answered already and nicely exchanged in the chat. Thank you, Philippe, for updating with the new documents. And now I'm passing the word to Costanza. That I should have prepared a nice introduction for Costanza, as nice as I prepared for other two presenters today, but unfortunately it's unexpected events, so please let me work on this. I'll do it in the end. While Costanza will now start question and answer session. Thanks a lot.
Okay, thanks to both speakers for the very clear presentations. So I will start with a question from Rodrigo Martinez from Pandela, who was asking how close we are to achieve quantum advantage for specific cases with quantum simulation. I don't know who wants to start.
I can take one.
Please go ahead, Elvira, and then we'll move to Leonardo.
Yeah, so well, let's start with quantum supremacy that was shown by Google in 2019, right? It was very exciting milestone for the community, but probably less exciting for the industrial sector, because it was shown that quantum can do much more faster certain types of computations than classical one, but those computations are useless for any practical purposes, for example. The next stage, what we consider as a milestone, would be the quantum advantage. What would quantum advantage for some practical tasks? For instance, I do believe that the closest one is, again, the simulations of the chemical systems, simply because at the current level of our, let's say, classical technology, we are already not able to simulate systems with more than 30-something spin orbitals. That would mean that if we will have quantum machines with good 30, 35, well, let's say 40 logical qubits, we will be able to tackle the problem that is not tractable by the most powerful classical HPCs simply because of its complexity. If you see the roadmaps published by the quantum providers, there was a QERA who published recently, Pascal announced yesterday, there's a Quantinuum and IBM who also kind of announced their roadmaps. This is something that will happen probably if everyone keeps the promise in between 28, 29, probably, maybe a little bit early, maybe a little bit later. We don't know, but we're just crossing fingers that it will be the case. From the algorithmical side, we already have some very good techniques that would allow us actually to use properly those machines and simulator systems. Now the question is, does the system of 30 spin orbitals, like which is literally a handful, like probably the CO2 molecule, represent the commercial value for like BMW or any industrial group, specifically the pharmaceutical ones who are tackling the problems of, for example, proteins systems with billion particles, or if you go to BMW engineers who works on batteries, we will ask you to simulate the surface reactions with 50 million atoms. Probably not. So after we actually show this quantum advantage, we will still have to ramp up on both hardware and software side in order to scale it up and tackle the systems that represents the business relevance. And after we've done that, probably we could be willing to consider how this technology might be integrated in the whole value chain, because with a new technology comes new constraints that might impact some production steps, etc. And yeah, so usually when our management asks us when we will see the hydrogen fuel cells optimized by quantum computer in production, and probably like in 10-15 years horizon.
Thanks a lot, Elvira. Leonardo, do you want to add anything?
Yeah, maybe I can add just a little bit on the side of analog quantum simulators. And in analog quantum simulators that are targeted on some specific applications. So quantum advantage has already been demonstrated a few years ago. So in some experiments with studying these kind of models that I've introduced before, these Hubbard models that are also interesting for the physics of temperature superconductivity. And it was demonstrated by benchmarking the results of the measurements on the device, on the atomic simulator, compared with theoretical calculation that I mean the two, the quantum simulator and the computation of the classical hardware were matching up to some point, and then at some point the classical calculation stopped to work because of accumulation of errors. Instead, the quantum simulator went on. So this was demonstrated a few years ago. But this is, I mean, just let me stress again that analog quantum simulators are problem dependent. So this does not mean that for other applications, so the quantum advantage should stay there.
Yes, I guess maybe if I could add something that also probably with photons, one can consider that quantum advantage with Gaussian Bose in sampling problems that are again a subclass, let's say, of simulations has been demonstrated or at least claimed in a science paper 2020, for instance, by Yang Pan from China. Yes. So I have a curiosity for Elvira. So I don't know whether you can address, if you can address it in this moment. But can you tell us just a few words about the hardware that's behind the computing and simulations that you were presenting?
Yeah, sure. So for this specific use case, we had access to two machines. One from Quantinum, it's ion trapped architecture, which is extremely precise, or at least the quality of the qubits is probably the best in the market right now. And the second one is IBM machines, which are, for instance, represent the largest in terms of number of qubits, but with a little, probably less quality than those of Quantinum. I skipped this part of how did we do simulations, so I just don't want people to think that like this entire huge 125 atom cluster plus oxygen were modeled on the quantum computer. We used classical fragmentation techniques in order to identify the most active part of this reaction that happens on the surface, identify, localize this fragment, and tackle this fragment using the precise quantum solutions. The rest was treated with a classical DFT, which worked pretty well because the rest of the molecular system was quite stable. And then they glued it back, hoping that basically the precision that we gain from tackling this most difficult and active part will actually overcome the fragmentation error, and in the end we will be better if we would treat the entire system with DFT as we do it right now, like with a state of the art. So it was the case. I cannot say or claim that it's a quantum advantage simply because like this small active part, you can still do it with a classical exact solution such as CSD, for example. But at least once machines are bigger, we can afford ourselves bigger active parts and bigger fragments. So the overall result could only be better. And that means that we have a very good promise and specifically a proven workflow, how we can actually scale up quantum solutions for chemistry using the classical fragmentation techniques to much larger systems.
Thanks a lot, Elvira. I guess that part of the question by Christophe was also addressed in your answer. So, and indeed, I think that your answer also relates very well with what Professor Fallani was mentioning in terms of co-processors, essentially, really like the importance of being able to combine the different computing and both analog, digital, and simulation techniques from the classical and quantum domain. So there's one question by Oscar Dietz on, I guess it is to Elvira. What was the role of AWS in the BMW Quantum Challenge?
So this challenge is the second edition. There was one in 2021, and we were happily partnering with AWS, who practically provided for free credits and access to AWS Braket services, Amazon Braket services. If some of you know, it's a kind of platform or marketplace where you can have access to different quantum computers, different quantum backends, in order to do your simulations or runs. So for those participants, we had a lot of companies who had access to their own means or their own quantum hardware, but there were some participants who don't unfortunately have this because it's quite expensive pleasure to get access to actual machines. And that's why we could claim some credits from AWS in order to benchmark their solutions for free.
Thank you. So there's one question by Philippe Granger directed to Leonardo. That is that what you were telling about the fact that quantum advantage was obtained several years ago in quantum simulations got so far less publicity and buzz than Google's or other quantum supremacy claims. Can you comment on that? Do you have any explanation?
Maybe I mean, probably I have a twofold explanation. One is on the line that I was mentioning before. So this was obtained in a kind of specific application, and the second one is maybe because it was obtained in an academic environment, and probably Google has higher capability of delivering messages to the world and to advertise the results. So I think that this is also part of can be part of explanation. And if I can, Costanza,
sure.
since I'm speaking, so I would like to. So there was a question before by Albert de Ruyter that asked why there was no collaboration, because this relates to something that I mentioned during my talk. No collaboration with the Netherlands. Actually, this is not true in the sense that I was just mentioning one project in the context of a quantum flagship that is a collaborative project that our group is part of, but is, of course, this is not the whole part of the story. So there are in the context of atom-based quantum simulators, there is research activity in Netherlands too, and actually there is one PhD student in my group that is now in Amsterdam in an exchange with the group in Amsterdam, and also what I was mentioning was connected just to one platform, and of course the quantum simulation and quantum technologies of course encompasses different architectures and different platforms, so this was not exhaustive at all.
Okay, I think that we are actually doing quite well with time, so we are about to reach the end of this session. So I would like to ask you if you have anything you would like to ask to policymakers in Europe as a wish, let's say, to foster further research on quantum simulation. What are the main obstacles that you see, whether they are really at the level of the fundings that are available, funding schemes, or whether there would be more need for, say, easier procedures and or other political hurdles that are in between us and the final uptake of this technology. And this, I think, could be a final question to both of you.
Oh, shall I start then?
Yes, please.
Oh, please go ahead, Leonardo.
Okay, so I would say that of course I mean we are now living in a period, so an historical period in which there is funding is we have funding from you in the context of different initiatives. So it's important that I mean, of course, quantum technologies in all their different branches and application areas are something that is I mean, so is giving results, but we have to think to this race for quantum in the long term. So it's important to keep the efforts and sustain the cause of quantum technologies also in the not only in the short term, but most importantly in the medium and long term. And there is, I think, an important point that that is not of easy and fast solution, but and this is also a point that is important in the context of a flagship, that is the point of education, in the sense that since all the quantum activities are becoming more and more important, both in academia and the industry, it is important to have people, quantum scientists and engineers that can work, and we know that nowadays it's difficult to find people, to hire people, because of the explosion of quantum initiatives, and so it's important to keep attention and be involved on the side of education.
Very good to hear this. As a coordination and support action of the flagship, we are trying to do our best in this direction. And on this, I would like also to take the note by Philippe to spread the fact that if you want to make publicity of some important academic achievement, you can also rely on our communication office. And here in the chat, you can find the email from 𝐀𝐠𝐚 by Sarah, who can help you on this. And Elvira, now?
I can only join Leonardo. So beside those like technological or operational, let's say, challenges, talents that has to be educated, probably I would also mention the management of expectations. Because somehow we're getting so excited about the progress, so we want more and faster. And every single paper or announcement in the internet right now, it's a breakthrough. So it becomes a little bit scary to kind of pass through or filter all those hype waves that are targeting the quantum computing community. So I would really, how to say, invite everyone to be patient. Technology needs to take time to get mature, and we are on a good path with a good speed. And yeah, please be honest in your approach.
Very good point, Elvira.
Thanks a lot. Yes. So I would like to finally thank both speakers and all of you for your attention. And the slides and the recording will be available to the registered participants. So we will make sure that this is done as soon as possible. With that, I think we can conclude this session. I don't know if Oxana, you have to add anything.
No, only thanks a lot to the participants, and a kind request to stay a couple of minutes after we turn off the recording and the guests are gone, so that we can have a little bit of chat. And I thank everybody. We have hold a lot of participants with us still, and looking forward to see you at the next session on the 4th of April, which will be about the future use cases of quantum technologies. Goodbye, everyone.
Bye.